Deep within the constellation Leo, far beyond the familiar stars that dot our night sky, a subtle shift in infrared light finally reached Earth after a century-long journey through the dark void. To the untrained eye, it appeared to be nothing more than another data set, just one stream of numbers among the trillions gathered by humanity's most powerful telescope. But concealed within that light was something the world was not prepared to see. It was a chemical signature belonging not to storms or rocks or oceans, but to life itself. The James Webb Space Telescope had detected a world so chemically alive and perfectly balanced that scientists achieved a level of certainty rarely seen in the field of astronomy. This wasn't a maybe. It wasn't a statistical possibility. It was a planet that appears fully habitable and, potentially, even more friendly to life than Earth. What Webb has found suggests more than just the possibility of life out there. It suggests we may have finally found it. The signal, the breakthrough, didn't come with a bang, but quietly, buried deep within infrared data collected as a distant planet eclipsed its star. As the starlight filtered through the alien atmosphere, specific wavelengths were absorbed, leaving behind a spectral fingerprint. Initially, scientists identified the usual suspects: carbon dioxide, methane, and water vapor. Each was significant, each suggestive. But then came the molecule that changed everything: dimethyl sulfide. On Earth, this compound is not produced by lightning, volcanoes, or geological chemistry. It is produced exclusively by living organisms. And the signal was not faint. It was strong enough that the probability of error dropped to less than 3 in 1,000. In a scientific field where uncertainty is the rule, this level of confidence is extraordinary. The super-Earth, the planet K2-18b, orbits a red dwarf star 120 light-years away, sitting directly in the zone where liquid water can exist. However, unlike the rocky, Earth-like world scientists once thought were necessary for life, this planet belongs to a different class entirely. It is a super-Earth, heavier, larger, and wrapped in a thick, hydrogen-rich atmosphere. And rather than making the environment hostile, that atmosphere might be exactly what makes it ideal for biology: stability and gravity. K2-18b isn't balanced on a knife's edge like Earth. Its environment appears remarkably stable. Surface temperatures hover around 120 degrees Fahrenheit, warm enough for liquid water, yet cool enough to prevent oceans from boiling off. This temperature is no accident. The hydrogen-rich atmosphere acts like a planetary blanket, trapping heat and distributing it evenly across the globe. Unlike Earth, where temperatures swing violently between day and night or summer and winter, this world likely experiences consistent, planet-wide conditions. Even on the night side, locked in permanent darkness due to tidal locking, the warmth remains sufficient to sustain liquid water. Gravity plays a vital role here. With a surface gravity nearly 3 times that of Earth, the planet holds onto its atmosphere with ease, preventing the kind of escape into space that doomed Mars billions of years ago. What seems extreme to us is actually an advantage. Strong gravity, a thick atmosphere, and stable temperatures create an environment where life doesn't have to fight for survival. Instead, it can focus on complexity, growth, and evolution over enormous timescales. The endless star, the star hosting this world, is a red dwarf, cooler and smaller than our sun, but far more enduring. While our sun will eventually expand and erase all life on Earth, red dwarfs burn steadily for trillions of years. This means any life that emerges on a planet like K2-18b has virtually unlimited time to evolve. The planet completes an orbit every 33 days, sitting close to its star, yet receiving almost the same energy per square meter that Earth receives from the sun. This places it squarely in the habitable zone, but with a crucial difference. The habitable zone around red dwarfs lasts far longer than around stars like ours. Add to that the thick atmosphere shielding the surface from radiation, and you begin to see why scientists are rethinking everything they believed about habitability. This discovery suggests that Earth-like planets may not be the best places to look for life after all. The universe may favor worlds that are bigger, warmer, and far more stable than our own. The living atmosphere. What truly elevates this discovery is the behavior of the atmosphere itself. The detected gases exist in a state of chemical imbalance. On a lifeless world, these molecules would react with each other and vanish. Yet, they persist in large quantities. On Earth, this kind of atmospheric disequilibrium is maintained only by biological activity. Life constantly pumping gases into the air, preventing it from settling into chemical stasis. K2-18b shows the same pattern. The absence of ammonia, a compound expected in lifeless hydrogen-rich worlds, strengthens the case even further. Something appears to be actively removing it. Something alive. If this interpretation holds, we aren't looking at a planet where life might exist someday. We are looking at a planet where life is already shaping the environment on a global scale, a living world breathing across interstellar space. A new blueprint. For decades, the search for extraterrestrial life followed a rigid blueprint. Scientists believed they had to find a planet identical to Earth. Similar mass, similar size, thin atmosphere, rocky surface, sun-like star. K2-18b shattered that entire framework in a single discovery. This planet is not Earth's twin. It is Earth's strange, oversized cousin, operating under rules we once assumed were hostile. With a mass more than 8 times greater than Earth's, K2-18b belongs to a class of planets known as super-Earths, worlds once dismissed as bloated, gas-heavy, and inhospitable. Yet, the data tells a different story. The planet's enormous gravity acts as an advantage, anchoring the atmosphere firmly in place and preventing the slow erosion that killed Mars. Its thick hydrogen envelope, once thought incompatible with life, creates a stable thermal environment that protects liquid water globally. This forces a profound shift in perspective. Habitability isn't about fragility and perfect balance. It may be about resilience, mass, and long-term stability. The most life-friendly worlds in the galaxy might not be delicate copies of Earth, but robust planets built to endure for trillions of years. The high sea and ocean. Beneath that hydrogen-rich sky lies what may be one of the most extraordinary environments ever discovered. Vast global oceans, potentially hundreds of miles deep, composed of water mixed with dissolved hydrogen under immense pressure. This is not an Earth-like ocean confined to shallow basins. This is a planetary ocean, a world-spanning liquid environment that dwarfs every ocean in our solar system combined. The presence of hydrogen fundamentally changes how this ocean behaves. Hydrogen dissolved in water expands the range of temperatures and pressures where liquid water can exist. On Earth, extreme pressure collapses biological structures. On K2-18b, hydrogen acts as a natural buffer, maintaining conditions suitable for chemistry and biology, even at staggering depths. This opens the door to ecosystems of unimaginable scale. Life would not be limited to coastlines or surface waters. Entire biospheres could exist layered through the depths, thriving in warm, chemically rich environments where energy is abundant. In such an ocean, evolution isn't constrained by scarcity. It is accelerated by abundance. The roar of life. Perhaps the most unsettling implication of Webb's observations is the sheer strength of the biosignatures. Dimethyl sulfide is not a molecule that lingers quietly. It breaks down rapidly under stellar radiation. For Webb to detect it from 120 light-years away, biological activity on K2-18b cannot be marginal. It must be planetary. This is not a world where life clings to isolated refuges. It is a world where life dominates atmospheric chemistry. The concentrations imply a biosphere operating at a scale far beyond anything humanity has experienced. Entire oceans metabolizing, breathing, and reshaping the atmosphere continuously. This isn't the faint whisper of microbial survival. It is the roar of a thriving planetary ecosystem. The atmosphere itself has become a living system, locked in disequilibrium, because biology is actively preventing it from settling into lifelessness. K2-18b doesn't just host life, it is shaped by it. The abundance. The implications extend far beyond a single planet. Red dwarf stars like the host of K2-18 they make up roughly 3/4 of the Milky Way. If even a fraction of their planets resemble this one, the number of potentially habitable worlds increases not by a factor of 2 or 10, but by hundreds. Worlds once written off as too massive or too hydrogen-rich are suddenly reclassified as prime candidates. The universe may not be sparsely populated with rare, Earth-like oases. It may be densely filled with super-Earth water worlds, each wrapped in thick atmospheres, each stable for trillions of years, each capable of hosting biospheres that mature far beyond Earth's current stage. The discovery forces a radical conclusion. Life may not be the exception. It may be the default outcome wherever physics allows for stability, water, and time. Hydrogen as fuel. For years, hydrogen-rich atmospheres were considered a dead end. Hydrogen was thought to be too light, too reactive, too unstable. On Earth, it escapes into space immediately. On K2-18b, it does the opposite. It dominates the atmosphere, creating a massive envelope that reshapes the planet's climate. This atmosphere doesn't just sit above the surface. It regulates temperature, pressure, and radiation. By trapping infrared heat with extraordinary efficiency, it eliminates the violent climate swings that challenge life on Earth. In this environment, biological systems aren't constantly forced to adapt to stress. They are free to optimize, grow, and diversify. The hydrogen atmosphere, once labeled hostile, emerges as the ultimate stabilizer, transforming K2-18b into a planetary incubator designed not for survival, but for flourishing. The metabolic engine. The chemistry of K2-18b tells a story greater than simple habitability. Methane, carbon dioxide, water vapor, and dimethyl sulfide coexist in combinations that shouldn't last. In a lifeless atmosphere, they would neutralize. That equilibrium never arrives because something is constantly injecting energy and matter back into the system. On Earth, biology plays this role, forests and oceans cycling gases. K2-18b shows the same signature, but on a scale that dwarfs Earth. The concentrations suggest biological dominance. Life is not a passenger here. It is the engine. The atmosphere behaves less like a static shell and more like a metabolic organ, processing chemicals in real time as a planetary scale biosphere breathes beneath it. Every transit observed by Webb reinforces this picture. This is a planet where life has already taken control of its environment and reshaped it into a self-sustaining system. The gift of time, perhaps the most underestimated factor in the emergence of complex life, is time. Earth has existed for 4.5 billion years, yet complex life appeared only in the final fraction of that history. K2-18b exists in a radically different context. Its star will burn for trillions of years. Evolution on K2-18b is not racing against extinction. It is unfolding at leisure. With stable temperatures and near-infinite time, life can explore evolutionary pathways Earth-based life never had the chance to attempt. Complexity is no longer constrained by catastrophic resets. K2-18b is not just habitable today. It may have been habitable for billions of years already, and may remain so long after Earth is gone. Redefining Earth-like. 4 generations. Earth-like meant rocky, temperate, and oxygen-rich. K2-18b forces a redefinition. Earth-like might not mean similar appearance, but similar outcomes. Stable temperatures, persistent water, and active chemistry maintained by biology. By those criteria, K2-18b may be more Earth-like than Earth itself. Our planet sits on the edge of multiple failure modes: runaway greenhouse effects, atmospheric erosion, and stellar death. K2-18b appears engineered by physics for longevity. It is a world designed to last. Tangible proof. Until now, the search for life was built on inference and statistics. K2-18b marks the moment those abstractions collapse into something tangible. This is no longer a philosophical discussion about whether life could exist. It is a scientific investigation into where it already does. The James Webb Space Telescope didn't just detect a planet. It demonstrated that we now possess the tools to identify living worlds across interstellar distances. This discovery is a proof of capability. Humanity has crossed a threshold. We are no longer speculating about life in the universe. We are beginning to catalog it. The easy path. One of the most disturbing implications is how effortlessly K2-18b seems to support life. On Earth, habitability feels accidental, almost precarious. On K2-18b, the conditions appear inverted. Habitability looks like the natural outcome of the planet's structure. The thick atmosphere smooths out extremes. The gravity locks everything in place. Nothing suggests life is on the brink of extinction. The physics itself seems tuned to keep biological processes running. This reframes life not as a rare miracle, but as a predictable consequence of stability and chemistry. K2-18b doesn't look like a lucky exception. It looks like a template. Life in 3 dimensions. When we imagine alien life, we picture organisms clinging to a surface. K2-18b suggests something more expansive. With deep oceans mixed with hydrogen, life wouldn't be confined to a thin layer. Entire ecosystems could exist vertically, stacked through pressure gradients and chemical layers. Some organisms might thrive near the surface, while others exist far below, feeding on chemical energy. This creates a volumetric biosphere, a living planet in 3 dimensions. What we are detecting may be only the exhaust of a much larger, hidden biological machine operating beneath the clouds. The late arrival. Perhaps the most unsettling thought is this. K2-18b might not represent the beginning of extraterrestrial life, but a mature chapter in a story that started long before Earth formed. If life emerged there billions of years before it did here, then Webb is detecting the signature of a biosphere that has passed through evolutionary stages we haven't yet reached. We are discovering life at the moment it begins. We may be arriving very late, tuning into a planet that has been alive, stable, and evolving long before our own world cooled enough to support microbes. Life in balance. What if these biosignatures represent a mature biosphere, a system that has reached equilibrium? On Earth, we are still climbing toward that state. K2-18b may have reached it eons ago. A finished biosphere recycles efficiently and wastes little. The atmospheric chemistry observed could be the steady output of a system running smoothly for billions of years. If so, we are seeing life in balance, a planet that has solved the problem of long-term habitability. The new cosmos. For most of human history, the universe felt vast, cold, and silent. K2-18b changes the emotional texture of the cosmos. Space no longer appears empty. It appears occupied, structured, and alive. The distance of 120 light-years no longer feels isolating. It feels intimate. Life is no longer abstract. It is measurable, quantifiable, detectable. The universe has not suddenly become alive because of this discovery. It always was. What has changed is our ability to see it. And once you cross that threshold, once you accept that living worlds may be common and ancient, the cosmos can never look the same again. Conclusion. What the James Webb Space Telescope has revealed is not just a planet, but a complete reframing of our place in the universe. K2-18b is a stable, enduring world where life appears woven into the very fabric of the planet. Its atmosphere is active. Its chemistry is regulated. Its oceans are persistent. Life didn't struggle to exist there. It took hold and reshaped the world. For generations, we scanned the cosmos for a pale blue that looked like home. Instead, We found something far more profound, a world that doesn't look like Earth, yet may be better suited for life. This discovery tells us that nature doesn't need familiarity to create living systems. It needs stability, chemistry, and time. And the universe has an abundance of all three. This moment marks a turning point. We are no longer searching in the dark. We are reading the atmospheres of distant worlds and watching biology announce itself across the stars. From this moment on, every star you look at carries a new question. Not whether life exists out there, but how much of it is already waiting to be found. If this discovery changed the way you see the night sky, make sure to like this video, subscribe, and share it. Because the universe is no longer empty. It's just waiting for us to look. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.